The objective of today's lecture will enable you to understand the structure of alkenes, their relative stability, and some reactions for the preparation of alkenes. Students, let us start with the structure of an alkene. This is a molecule representing the structure of an alkene making two bonds, and you know that whenever a carbon atom is making a double bond, it is sp2 hybridized. Now let us look at the electronic density of an alkene. Whenever a carbon makes a double bond, you know it have to undergo hybridization, and which type of hybridization? It is sp2 hybridized. So sp2 hybridization means that three orbitals have undergone hybridization. So a carbon atom which is sp2 hybridized makes three sigma bonds, 1, 2 and the third one. The unhybridized p orbital then overlaps sideways to make a pi bond. So this is a molecule representing the electronic density of sigma bonds and pi bond in an alkene. Students, other structural feature of alkenes are that the carbon-carbon distance in an alkene is shorter, which is 1.34 angstroms, than the carbon-to-carbon bond in ethane, which is 1.54 angstroms. And this is due to the increased electronic density between the carbon atoms. This is a single bond of an ethane, which is having all saturated bonds, sigma bonds. The bond length between this carbon and this carbon is 1.54, whereas that of ethene making a double bond is 1.34. And the reason for the decreased bond length is the increased electronic density between the two carbon atoms. The nucleuses will apply a greater inward pull and therefore reducing the bond lengths. Students, one of the most important structural property of alkene is stereochemistry. Now, what is stereochemistry? It is the orientation of atoms or group of atoms in the three-dimensional space. Now, the carbon atoms in alkene, they are coplanar. What do I mean by saying coplanar? That the orbitals are present in the same plane, means x plane, y plane or z plane. And the rotation of one carbon atom with respect to the other is restricted. That is why the isomerism, which is called cis and trans isomerism, they exist in alkenes. Now, what are trans isomers? In which the identical groups are present on opposite sides of the double bond, whereas cis isomers are those in which identical groups are present on the same side of the double bond. Now, these p orbitals which you can see in cis and trans isomers, they are coplanar, means either they are present on the y-axis or they may be present on the z-axis. Students, you know that the pi bond is formed by the sideways overlap of the two p orbitals which are coplanar to each other. Since the sideways overlap is between the two coplanar p orbitals, that is why the free rotation across this double bond is restricted. So, the group of atoms or atoms which are above this double bond will remain on their position, and the group of atoms or simple atoms below this double bond will always remain at their fixed position. So the free rotation is restricted. So cis and trans isomerism is possible in alkenes and not in alkanes. The next topic of today's lecture is the relative stability of alkenes, and there are three factors which influence the stability of alkenes, which are the degree of substitution, stereochemistry and conjugation. Now let us discuss each of them in detail. Students, the first factor is degree of substitution. Now, what do I mean by saying degree of substitution? Means how many alkyl groups are present across the double bond. Now, when alkyl groups are present across the double bond, then highly alkylated alkenes are more stable as compared to less alkylated alkenes. Let us understand this phenomena by examples. Look at this first molecule. Now, students, you know that this area of high electron density which contains a sigma bond and a pi bond, it acts as a nucleophile. You already know what is a nucleophile, means a species which can donate a pair of electron. So now this is the reactive site of alkenes, which is protected by all these alkyl groups from all sides. You know that methyl groups, this carbon atom is sp3 hybridized, making 4 bonds with a tetrahedral geometry. All these methyl groups are going to protect this double bond, which is the area of rich electronic density. So this alkene will be unable to react due to crowding, steric hindrance. That is why it will be more stable and less reactive. Now let us look at the example of the second molecule, in which you can see that I have replaced one methyl group by a hydrogen atom over here. Now a little less steric hindrance have been reduced. So the nucleophile over here, it can easily approach the electrophile from one side. So as compared to this highly alkylated alkene, this a little less alkylated alkene will be a little more reactive. Similarly, look at the next example, in which I have replaced another methyl group with a hydrogen atom. I have reduced the further crowding, and this nucleophilic region is now more exposed, so it can react easily with an electrophile. So alkylation provides crowding across the double bond, and it makes the alkene less reactive and more stable. The second factor that affects the stability of alkenes is stereochemistry. Now students, trans alkenes are more stable as compared to cis alkenes. This is due to the reduced interaction among the alkyl groups. Now look at these two stereomeric isomers. The first one is trans. Now you can see that identical groups are present on the opposite sides of the double bond. This methyl, which is going to have a tetrahedral geometry, now it is going to feel a little less steric interaction because on the other side a very small hydrogen atom is present. Whereas if you compare this side of trans with cis molecule, you will see that two sp3 hybridized a tetrahedral geometry methyl groups are present on the same side, which are going to interact with each other, provide greater crowding on one side, and hence steric interactions are going to develop, making cis structure less stable as compared to trans structure. Students, how this reduced steric interaction develop stability in a molecule? In a cis structure, you can see that these two methyl groups, they are going to interact with each other. This steric crowding over here on this double bond is going to affect the stability of the pi bond and is going to react in order to convert the more reactive pi bond into a more stable sigma bond. But such type of interactions are not present in the trans structure because these two bulky groups, they are far apart from each other, and hence they are not going to produce their effect on the double bond and giving more stability to trans structure as compared to cis. Students, the third factor that affects the stability of alkenes is conjugation. Now what is conjugation? The word conjugation is derived from a Latin word that means to link together. In organic chemistry, it is used to describe the situation that occurs when p system, means the p orbitals, are linked together. In simple words, you can say conjugation means alternating single and double bond. Now it happens sometime that alternating single and double bonds are not present. So, an isolated p system exists only between a single pair of adjacent atoms, means a single pair of a double bond. And an extended p system exists over a longer series of atoms. For example, alternating single bond, double bond, single bond, and double bond. We are going to discuss isolated and extended system in the next lecture, but over here we are going to discuss conjugation. In order to understand conjugation, look at this example in which you can see alternating single bonds and double bonds. Let us look at the structure in which the p orbitals are shown. You know that p orbitals, they overlap sideways in order to make a pi bond. Similarly, the second p orbitals of this double bond are going to overlap sideways. If these all the orbitals are coplanar, means they are present in the same plane, maybe y plane or z plane, then there is a possibility then that these two p orbitals might also overlap with each other. So whenever there are double bonds and single bonds in conjugation, means alternating positions, then this p system is extended throughout, providing stability to the molecule. Let us look at an example to make a comparison between isolated system and conjugated system. So students, 1,3-butadiene is more stable as compared to 1,4-pentadiene. Why? Because 1,3-butadiene is a conjugated system having alternating double bond and single bond. So the p orbitals, they will be extended throughout the system. Whereas in 1,4-pentadiene, you can see that the double bond is not in alternating fashion with the single bonds. Double bond, single bond, and then the double bond. Whenever double bonds are present in such a way, the system is called isolated, because these p orbitals of the double bonds, they cannot interact among each other. Therefore, it is an isolated system and it is less stable as compared to conjugated system. Now students, please make a correction in your book in which the structure is given, which is 1,4-butadiene. It is a wrong structure. Instead of it, you have to write 1,4-pentadiene. Students, in the next topic, we are going to study the methods for the preparation of alkenes, means the reactions through which we can prepare alkenes. Two of the methods we are going to study today. The first one is dehydration of alcohols and the second one is dehydrohalogenation of alkyl halides. The first method for the preparation of alkene is dehydration of alcohols, and students, you know that dehydration means removal of water molecule. So we are going to remove a molecule of water from an alcohol to produce an alkene. Now the alcohol molecule is going to remove a hydroxyl group and a hydrogen atom from adjacent carbon atoms when it is heated from 340 to 450 degrees Celsius in the presence of aluminium oxide. It gives an alkene and a water molecule. Let us understand this chemical reaction. You already know what this half-headed arrow means, the transfer of a single electron. When it is heated, then this hydroxyl group and H, this is going to make a bond producing a water molecule, and the other two electrons, they are going to transfer over here. They are going to make a pi bond because already these two carbon atoms are sigma bonded. So the next forming bond between already bonded sigma atoms is a pi bond. Therefore, heating alcohol causes dehydration, removal of water molecule, producing an alkene. The other chemical reagents that you can use instead of aluminium oxide are phosphorus pentoxide, sulfuric acid, phosphoric acid. They are also used for dehydration of alcohols. Now students, you already know about tertiary, secondary and primary structures. The reactivity order of tertiary alcohol is greater than secondary alcohol, and secondary alcohol is having greater reactivity as compared to primary alcohol. Now just to recall, tertiary alcohols are those in which the carbon to which the OH group is attached will be further attached with 3 carbon atoms. In secondary alcohol, the carbon to which the OH group is attached will be connected to 2 other carbon atoms. And in primary alcohol, the carbon to which the hydroxyl group is attached is further attached with 1 carbon atom or none. So this is an example of primary alcohol. And the reason for this reactivity order is again the steric hindrance. More the crowding, greater is the reactivity, less is the stability. Students, keeping in mind the reactivity order, compare the reagents that we are going to use for the dehydration of secondary alcohols and tertiary alcohols. Look at the structure of secondary alcohol. The carbon to which the hydroxyl group is attached is further attached with two carbon atoms. The conditions for dehydration are 75% sulfuric acid, heating from 140 to 170 degrees Celsius. It is going to give an alkene along with the water molecule. The conditions for tertiary alcohol dehydration are 20% sulfuric acid. Now you can see it is a more diluted reagent. Why is it so? Look at the structure of tertiary alcohol. The carbon to which the hydroxyl group is attached is further attached with three carbon atoms. So this structure is relatively less stable because of the crowding and more reactive. Since it is more reactive, then we do not have to provide drastic conditions. It can react under mild conditions, giving an alkene along with water. But secondary alcohol, it is less reactive as compared to tertiary, so it needs drastic conditions. The second method for the preparation of alkenes that we are going to study today is dehydrohalogenation of alkyl halides. Means that we are going to remove a hydrogen and a halide atom upon heating with alcoholic potassium hydroxide. Let us look at the chemical reaction, and the examples are given in your textbook. This is a alkyl halide. Why? Because this is an alkyl group and over here an X atom is present which is representing a halide. It can be chloride, bromide, iodide. Now, in the presence of alcoholic potassium hydroxide, which will cause dehydro means removal of hydrogen, halogenation means removal of X atom from adjacent carbon atoms, producing an alkene along with potassium halide and water. Now, the potassium from potassium hydroxide is going to react with this halogen atom over here, giving potassium halide, and this hydrogen is going to react with the hydroxyl group of potassium hydroxide, giving rise to a water molecule. Similarly, students, you can observe the same phenomena in rest of the examples. Students, before going into the reactions of alkenes, let us study the reactivity of alkenes. There is a relatively diffused region of high electron density in alkenes as compared to alkanes. This is due to the presence of pi bond, since an ethene pi bond is weaker than the sigma bond. Why? Because sigma bond is under the influence of nucleus. The nucleus have a tighter hold on the sigma electrons as compared to pi electrons. Therefore, it requires less energy to break. Hence, the reaction of alkenes involves the weaker pi bond and electrophilic addition occurs. Why? Because this pi bond acts as a nucleophile. So, anything which adds to it, it will be a electrophile. It involves a change of a pi bond to a sigma bond through addition reactions. Means something is going to add across the double bond in order to convert into a single bond. Students, that we know the reactive site of alkenes, let us study their chemical reaction. The first one is hydrogenation. Hydrogenation is a process in which a molecule of hydrogen is added to an alkene, means where the pi bond is present in the presence of a catalyst to give a saturated compound. This process is known as catalytic hydrogenation. It is a highly exothermic process. The catalysts employed are platinum, palladium, and rhenane nickel. The amount of heat evolved when 1 mole of alkene is hydrogenated is called heat of hydrogenation, which for 1 mole is equal to 120 kilojoules per mole. This process is used in the laboratory to convert vegetable oil into vegetable ghee. As hydrogenation involves the addition of hydrogens across the double bond, so we need to have freshly prepared hydrogen, which is called rhenane nickel, and it is prepared by treating nickel aluminium alloy with caustic soda, which is sodium hydroxide. An aqueous solution of sodium hydroxide is treated with nickel aluminium alloy, which gives rise to freshly prepared hydrogen. That hydrogen is added across the double bond in the presence of nickel as a catalyst, and you can see it is going to give you a saturated compound. This molecule of hydrogen is going to add across this double bond one hydrogen each to the carbon atom. So this molecule converts from 3-methyl 1-butene to isopentane, or you can say it is 2-methyl butane. The second example of hydrogenation is conversion of benzene into cyclohexane. As we know that benzene have 3 double bonds, so 3 moles of hydrogen molecules are needed for the hydrogenation of 1 mole of benzene into cyclohexane. Look at the chemical reaction. Each of the hydrogen molecule is going to add across the 3 double bonds over here in the presence of nickel as a catalyst, giving rise to cyclohexane, converting an unsaturated hydrocarbon to a